There you go. So for the recording, I'm saying again, we're going to start the day by listening to Jack from Natural P giving us an introduction to cosmic neutrino background.
Okay, so can everybody see my slides?
Yes.
Fantastic. Right then, so first of all, thank you for having me. Today I wanted to give you all a very brief introduction to the cosmic neutrino background. I won't be going through a great deal of my research here, but I realise that this is one of those topics that maybe quite a few people have heard of, but not that many people know a great deal about. So I think it'd be nice to start from the very beginning and just give you a brief introduction. So today I want to give you, I want to go through a few things. First, I want to discuss from the beginning, what is the CNEB? Then I want to introduce maybe why we're interested in its detection, and then give you a brief overview as to how we might actually go about detecting it. So starting from the beginning, what is the CNEB? And what I hope to build up to in this talk is this figure here. So right now it seems a little bit daunting, but I'm going to break it down step by step, and by the end, hopefully everything in here should be fairly clear. So starting from the very beginning, or at least the beginning of this talk, we're just starting just a little bit after inflation, the electroweak symmetry breaking, and after all these QCD bound states have formed, where we've got a thermal bath consisting of just electrons, photons, and neutrinos, and these are all at a temperature which we're going to call TSM, the standard model temperature. And these are all held in equilibrium. So electrons and photons are kept in equilibrium through electromagnetic interactions. So we have, say, Compton scattering, and we also have pair production and annihilation. So yeah, we have neutrinos and electrons, which are kept in equilibrium through weak interactions. So we can have charge current and neutral current interactions, and we can also have, again, pair annihilation and pair production. And of course, neutrinos and photons are kept in equilibrium indirectly through their interactions with electrons. As the universe expands and cools a little bit, we get neutrino decoupling. This freeze out happens when the rate of neutrino interactions is equal to the Hubble parameter, and this corresponds approximately to the point at which neutrino interactions take about the age of the universe to proceed. The neutrino interaction rate can be written approximately as the neutrino interaction cross-section multiplied by the neutrino number density, where the neutrino interaction cross-section is given by GF squared. So this is the Fermi constant multiplied by the temperature squared. And you can see this temperature squared dependence just by, say, looking at dimensional analysis. The neutrino number density, if we assume a Fermi-Dirac distribution, is given by the integral over this distribution, which we find comes out to be approximately proportional to the temperature cubed. So we can go ahead and we can plug that all in, and we find that the neutrino interaction rate goes like GF squared times by the temperature to the 5th power. The Hubble parameter from the Friedmann equation goes like Gn times the energy density of the universe, where this energy density is given by the sum over all of the relativistic degrees of freedom. So this is during radiation domination. So we sum over electrons, photons, and neutrinos, and we sum over their equilibrium distributions, which are Fermi-Dirac and Bose-Einstein, and we augment those by a factor of the momentum because we're interested in the energy density rather than the number density now. You go ahead and you perform this integral and you find something that goes like temperature to the 4th power. So the Hubble parameter squared goes like the gravitational constant Gn multiplied by the temperature to the 4th power. So we can rewrite our freeze-out condition in terms of the decoupling temperature and these coupling constants like so. We go ahead and we find that the decoupling temperature then is approximately 1 mega electron volt. It's slightly more than that when you include all the other factors, but it's around about 1 mega electron volt. And during radiation domination, we know that the Hubble parameter goes like 1 over 2T. So we can go ahead and we can solve for the temperature in terms of the Hubble parameter, which we know. And we find that this decoupling happens about 1 second after the Big Bang. So returning to our timeline, we know that this neutrino decoupling happens at about 1 second and about a temperature of 1 MeV. And what we're left with after this decoupling is now 2 thermal baths. So we've got neutrinos, which go off on their own. And these will later become what we call the cosmic neutrino background. And we're left with a thermal bath of now electrons and photons that are kept in equilibrium. And these photons will go on to go on to what we call the cosmic microwave background, the CMB, which you're probably much more familiar with. Importantly, though, at this point, they're still at the same temperature. So even though the neutrinos have decoupled, these 2 thermal baths go on at the same temperature. But we're about a temperature of 1 mega electron volt, and as the universe expands and cools a little bit further, we get another important process that takes place. So the electrons and positrons start annihilating to photons. So above a photon energy of 1.02 mega electron volts, so this is about twice the electron mass, we can have electrons, positrons annihilating to photons, but equally we can have photons pair producing electrons and positrons. But as the temperature drops below 1.02 MeV, we can only have the forward process. Electrons can only annihilate to photons and not the other way around. And this is important because it changes the photon temperature. So without proof, but please feel free to ask me about this at the end or on Slack or something later, we can show that in a co-moving volume, the total entropy is conserved, which means that before and after this annihilation process, the entropy needs to be the same. This condition can be written like so, again, without derivation, but I'm happy to go through it at the end, as the entropy density multiplied by something that looks like the volume is this expression here. So this is the number of relativistic degrees of freedom that contribute to entropy, this G. I don't know if you can see my cursor. And this is the temperature. And this needs to be the same after annihilation, where in general, the number of relativistic degrees of freedom is given by the sum over the relativistic degrees of freedoms in bosons plus 7/8. So this 7/8 factor comes from the different distribution functions multiplied by the relativistic degrees of freedom in fermions. So before annihilation, we have 2 degrees of freedom from photons. These are the 2 polarization states, plus 7/8 multiplied by the number of degrees of freedom in electrons. So this first 2 comes from the fact that we have electrons and positrons, and the second comes from the fact that we have 2 helicity states. And after annihilation, of course, we sum, this sums to 11 halves. And then after annihilation, we only have photons. We just have these 2 polarization states. So this entropy conservation condition can be rewritten like so. And we can go ahead and we can solve this for the photon temperature in terms of this original standard model temperature. But of course, recalling that neutrinos are still at the standard model temperature, we can write this as a condition on the neutrino temperature. And we find that neutrinos today exist at a temperature that's slightly lower than the photon temperature. And this is quite an important expression for anybody that's studying the cosmic neutrino background. So returning to our timeline, just after this annihilation process, we now have photons that are at a different temperature to the neutrinos, and there's pretty much only photons in this thermal bath. As the universe expands and cools a little bit further, about 1 minute after the Big Bang, we get Big Bang nucleosynthesis. So this is where the universe is cool enough such that protons and neutrons that were previously floating around freely can start to pair up and form some of the heavier elements. And then a little while later, 10 to the 5 years later or so, the universe becomes cold enough that electromagnetic interactions more or less freeze out, and the universe becomes transparent to photons. And what we're left with is what we call the cosmic microwave background, the CMB, which is currently the furthest that we can look back through time. So extrapolating forward to the present day, we now have 2 thermal baths, one at T nu naught, which is the cosmic neutrino background, and one at TCMB, which is photons, and we call this, of course, the CMB. So today, the cosmic neutrino background exists at the temperature T nu naught, which is related to the temperature of the CMB by this temperature here. We go ahead, we plug in the numbers, and we find that the cosmic neutrino background is at a temperature of about 0.168 milli-electron volts. Importantly, this means that at least 2 of the neutrino states are non-relativistic. So we know from neutrino oscillation experiments that neutrinos have got mass, and we know what the mass splittings are between those states. So even if the lightest state is massless, the other 2 will have a large enough mass that they will be non-relativistic. And secondly, these exist today as freely propagating mass eigenstates. So they're produced in weak interactions in the early universe, but they've existed for so long that they've undergone decoherence, and now they exist as mass eigenstates rather than the flavor eigenstates that we typically talk about in weak interactions. We expect that these will follow their equilibrium distribution, which is this Fermi-Dirac distribution, at a temperature T nu naught, which if we go ahead and integrate over, we find that a number density of about 56 per cubic centimeter. As we'll see later on, this is quite a large number. And importantly, these should all be left helicity states. So in the standard model, you're probably aware that we only have left chiral fields. And these things were produced ultra-relativistically, and in that limit, helicity and chirality overlap. So they were also produced as left helicity states, And since helicity is a good quantum number, since the helicity operator commutes with the Dirac Hamiltonian, we find that in the absence of extra interactions, this helicity should be conserved, so they should all be left helicity states still today. But the way in which the cosmic neutrino background fundamentally differs from the CMB is that neutrinos have mass, which means that they may cluster. So you may end up with something that looks like a cold dark matter profile. You may end up with overdensities. So this is where you have a number density that's slightly larger than this number density, 56 per cubic centimeter. And you also get something which I call helicity mixing here. So even though we expect that they may all be left helicity states, because they have mass, they can have gravitational interactions, which can go ahead and change their momenta. And if you change the momenta, you can change the helicity profile. And what you tend to find is if you have significant gravitational interactions, rather than having just left helicity states, you can have, say, a 50-50 split of left and right helicity. So next, I want to move on to answering the question as to why we're actually interested in detection. Now, hopefully that should already be somewhat clear from what we've already discussed, but I want to spell it out in detail. So, as I've already mentioned, the cosmic microwave background is currently the furthest that we can look back through time. And this occurred about 300,000 years, 400,000 years after the Big Bang. The cosmic neutrino background, on the other hand, is from about 1 second after the Big Bang. So if we can observe the cosmic neutrino background, we can look back significantly further through time. And importantly, of course, it dates back to before Big Bang nucleosynthesis, whereas the CMB is after. So if we can get an insight into the CNUB, we might also get an insight into BBN. It's also a rare source of non-relativistic neutrinos. So to my knowledge, it's one of only 2 non-relativistic neutrino sources, and it's certainly the one with the biggest number density. And seeing as we've never detected a non-relativistic neutrino before, they may have extra interactions at low energies, or they may behave completely differently at low energies. We don't know. And we can also, we're also naturally sensitive to the mass. So if we detect a non-relativistic particle, we're naturally sensitive to the mass scale, which is something that we currently don't know for neutrinos. And then perhaps most excitingly, maybe these neutrinos aren't there at all. So maybe neutrinos are unstable, or maybe the thermal history is just completely different. And they were never produced in the first place. We don't know. And until we try and detect them or whatever, we're not going to know. We're not going to know. So that can all sort of be boiled down into this picture here. So we just put a big red question mark on the timeline and say, well, yeah, we think we know what's going on, but certainly there are a lot of questions. And until we've actually observed it, we can't say for sure that this is what happened. So if they're so exciting, then why haven't we detected them yet? So neutrinos are notoriously difficult to look for. So what I show here is a typical neutrino scattering cross-section. It goes like GF squared times by some sort of energy scale squared. And if you go ahead and you plug in the numbers, you get that this comes out to be about 10 to the minus 50 centimeters squared. And this is even lower for relic neutrinos, where this energy scale is of order the neutrino mass, which is really quite small. Is this a small cross-section? Well, let's compare this to a typical electromagnetic process. So this is the cross-section for electron-positron annihilation to a pair of muons. We find that this comes out to be about 10 to the minus 25 centimeters squared. So these neutrino cross-sections differ by about 25 orders of magnitude, if not more. So these really do interact weakly. And then even worse for relic neutrinos, because they're such low energy, we might not be able to detect them at all. So typical neutrino detection experiments have thresholds. Take, for example, this inverse beta decay process, which is commonly used in neutrino detection experiments. This has a threshold of about 1.8 mega electron volts. Of course, for relic neutrinos, we've got about 0.1 milli electron volts. We're absolutely nowhere near meeting this threshold to be able to detect them. But there is some hope. As I mentioned earlier, there are a lot of these relic neutrinos. So if we can find a way to get them to interact, it shouldn't be too difficult to see them. So what I show on this plot is the fluxes from 2 different sources. So I have on the right-hand side some solar neutrinos in this black and this orange curve. And then in this blue curve, I've got relic neutrinos. And as you can see, there are a lot more of those than there are of solar neutrinos. And then just for completeness, I show the detection thresholds for some existing neutrino experiments. And as you can see, those are nowhere near capable of detecting relic neutrinos currently. So the last thing I want to very quickly go through is how we might actually go about detecting the cosmic neutrino background. So far we've identified 2 problems. The first, of course, is the threshold. We need to get these neutrinos to interact in the first place. There are 2 ways to go about solving that issue. The first one, of course, is to find a process that has no threshold, which would immediately remove the problem. And the second is maybe to add some energy to our experiment and find some way to bridge this threshold. The second difficulty is the event rate. So these cross sections are typically tiny. So in order to detect them, we need to either use a huge number of targets in our detector, or we need a large cross section. We need to find a process that has a large cross section or some sort of huge enhancement that we can exploit in order to get a decent event rate. And to that end, there are several experiments that have tried to, or have been proposed to detect the cosmic neutrino background. The first and perhaps most well known is the Ptolemy experiment, which was first proposed, or at least the idea was first proposed by Weinberg back in 1962. And this utilizes neutrino capture on tritium, leaving an electron and a helium-3 ion in the final state. Now, this process is interesting because it has no threshold at all. So because tritium is a natural beta decayer, if you move the neutrino to the right-hand side of this expression, you can naturally have that process. You can naturally get a beta decay of tritium to an electron, a neutrino, and a helium ion, which means if you move the neutrino to the left, you can capture this neutrino at any energy you want. The difficulty, of course, is that because you have natural beta decays of tritium, you have large backgrounds, and it can be hard to distinguish the electrons that come from the tritium beta decay from those that come from neutrino capture. Second option, which is also thresholdless and has been discussed for quite a while by quite a few authors, is this coherent scattering process. So you take a neutrino, you scatter it off some target, which I'll call X, which could be, say, a nucleus or an electron, and you're left with a neutrino and the same thing in the final state. The exciting thing about this is because neutrinos are at such low energy, they have really large wavelengths, and it means they see more targets in the detector when they scatter off of it. This leads to enhancements, which can be, say, of order 10 to the 20 or so in the cross-section, which is absolutely huge and gives us good hope for maybe detecting them. And then the last thresholdless process that I want to discuss is something called the Studolsky effect. So hopefully you're all familiar with the Zeeman effect, which is where if you put an electron in a magnetic field, the energy of the two spin states is split. The Studolsky effect is very similar, except rather than coupling the electron to a magnetic field, you're instead coupling it to a background of neutrinos. And this effect is a lot smaller than the Zeeman effect, but there are certainly some ideas as to how you might be able to see it. It's quite exciting, actually, because today, I believe, is the 100th anniversary of, I think, the publication of an explanation for the Zeeman effect. So this is I found it, say, about half an hour ago. It's just a bit of a coincidence. Okay, and then for some processes that have some thresholds, about a year ago, I worked on an idea where we could use an accelerator experiment to detect relic neutrinos. So as I've already mentioned, these things are at super low energy in the lab frame, and they have some threshold to overcome with some experiments. But what you can do to potentially overcome this threshold is basically a change of frame. So if you have a target at rest, you try and capture neutrinos, you've got almost no energy. But if you run a beam through the neutrino background, so say a high energy accelerator beam with the protons or some heavy ions on it or something, in the rest frame of those ions on the beam or those protons on the beam, the neutrinos have some energy. And if you put your beam energy high enough, these things can have enough energy to cross some threshold. And more excitingly, because you're able to tune this energy of your beam, what you can do is you can even exploit a resonance to get a huge enhancement to a cross section. I don't want to go into too much detail here because it's quite a complicated idea, but nevertheless, it's exciting. Another proposal that's been about since the 90s is that you could use ultra-high energy cosmic rays to detect relic neutrinos. So this idea is you have these cosmic neutrinos floating around. You scatter some super high energy cosmic ray neutrinos. So this is one that comes from maybe a supernova or a black hole or a quasar or some sort of astrophysical source. And it scatters with just the right energy such that it hits this neutrino at the Z resonance and produces these Zs on shell. At this energy, this cross-section is massively enhanced. So what you would look for is you'd observe your high energy cosmic neutrino spectrum, and you'd look for a dip in the flux at this very specific energy, which I think is of order, say, 10 to the 21 electron volts. It's absolutely huge, and we've never observed a neutrino at that energy, but if you could, then you'd look for a dip, and maybe this would give you some indirect evidence for relic neutrinos. But of course, this is quite challenging. And then last of all, more recently, there's been this proposal to detect them using the exclusion principle. So if you have some sort of process or some sort of decay that gives rise to very low energy neutrinos, because the cosmic neutrino background exists and it fills up all of these low energy states, the neutrinos that come from this decay process could be Pauli blocked. So because of the exclusion principle, they have no states free, no states available to them. So you see a suppression in these processes. So what you would do is you'd look at the decay spectrum of things, and then you basically see an absence of low energy neutrinos from them. So just to very quickly summarize, the cosmic neutrino background is currently the furthest that we can look back through time, and detecting the CNEB could reveal a wealth of new physics. But of course, this detection is made very difficult by the neutrino properties, and in particular for the cosmic neutrino background, where the energy is very low. But there are a lot of exciting proposals to detect the CNEB. So the last thing to do is to say thank you and ask if there are any questions. Just for reference, if anybody would like to go through this on their own or use this for some sort of revision or whatever, then the slides are available on the Indico page. Thanks a lot.
Thank you very much, Jack. And let's give him a round of applause. Perfectly on time as well. I completely forgot to give you the reminders, but you were 20 minutes on the clock. So that's impressive.
Yeah.
So yeah, just.
Thanks a lot.
Yeah, so now we will move on